Here you see a group of foods that are very high in what we call fats. Fats are based upon a group of lipids called the triglycerides. Let's take a look at how triglycerides are put together and how to take them apart. First of all, to make a triglyceride, you begin with a glycerol molecule that has 3 hydroxyl groups attached to it. And to it you attach 3 fatty acids. Fatty acids are basically long-chained hydrocarbon carboxylic acids, usually somewhere between 17 and 22 carbons in length. We begin by removing 3 water molecules. You can recall that those are called condensation reactions. So we'll produce 3 water molecules, and in addition, something that contains 3 ester groups, a triester. This molecule is called a triglyceride. Now the R groups that are attached can be the same or differ. Here from your IB data booklet is an example of several R groups, fatty acids. Some of these molecules are saturated, some of them unsaturated with multiple bonds. In the example I've provided here below, we can see the triglyceride that I've made consists of 3 saturated fatty acids. I can recognize that because I see only single bonds. The length of the carbon chains, however, differ. The one in the center is palmitic acid, as it's only 16 carbons in length. And on the right-hand side, both of those are stearic acid, which contains 18 carbons. So those groups can be the same or they can be different from each other. If I want to reverse the process, I often need to employ either an acid to help break it apart, or I need to employ a biological catalyst, in this case lipases, to provide the reverse, which is called hydrolysis. Now let's take a look at the structure a little bit more carefully. If I begin with saturated fatty acids, I produce long-chain triglycerides that are relatively linear in shape. Because they're linear in shape, they tend to stack well together with lots of overlapping surface area and surface contact. That then enhances the London dispersion force that can form between them. Such materials tend to be solids at room temperature, and you might recognize them as lards. However, my chain can also have unsaturated double-double bonds that are in it. In this particular molecule, it's considered to be polyunsaturated because it has many multiple bonds. Now, you'll notice that the orientation of some of these bonds, double bonds, slightly differ. Let's begin by taking a look at the red end of the molecule. You'll notice that the carbon-carbon chain, in this case, continues on opposite sides of the double bond. This is called a trans fatty acid. I can also have the groups continue on the same side of the molecule, in which case they're called cis fatty acids. Cis fatty acids cause a kink in the linear chain, deviating it from a linear form, whereas the trans fatty acid tends to maintain the linear form of the molecule. Trans fatty acids are somewhat unhealthy for us. Now, I would like to bring up a point here that single bonds don't exhibit this type of isomerism. It's very easy to grab a particular molecule and you can rotate about the single bond. This is not the case with double bonds. Double bonds do not allow rotation, whereas single bonds do. The cis fatty acid, as I mentioned, leads to a situation with kinks in the chain, and that thereby distorts the amount of stacking and how easily the molecules can fit together. This reduces the London dispersion force. And as a result, many of these substances are liquids at room temperature, and you might recognize them as vegetable oils or peanut oils. I'd like to look at something called an iodine number. An iodine number is a measure of how unsaturated a particular hydrocarbon might be. In particular, it looks at the grams of the I2 molecule that you would need to add to 100 grams of a fat. So here's an example of a fat. You'll see in it it's got some multiple bonds. The fact that I have 2 double bonds here indicates that this particular substance could take on 2 iodine molecules, each of those double bonds opening up and accepting an iodine on each end of the double bond. So to balance it, I'm going to require 2 iodines to balance this. If I just start with the chemical formula, I can also recognize how many iodines I need to add. So if I write down here a chemical formula, I can recognize that with 18 carbons, it should hold up to 37 hydrogens if it was saturated. Here I notice it's 4 short. Therefore, I can tell it must have 2 double bonds in it, therefore requiring 2 iodine molecules to balance. Here I've shown the complete balanced chemical equation. Now, to determine the iodine number, I begin with 100 grams of the fat, and with knowledge of its chemical formula, I can determine its molar mass. Using those 2 bits of information, I can calculate the number of moles of my fatty acid. From the balanced chemical equation, I see a 1:2 ratio exists between the 2. So I double the amount of moles I have of the fat. And now I'm going to convert that mole back into mass by multiplying the molar mass of I2, not just I, the I2 molecule. And that gives me 172 grams. So I could say the iodine number for this particular fat would be 172. The bigger your iodine number, it tends to indicate more and more double bonds that are present. And of course, something that has a 0 iodine number would already be saturated. Fats also have a limited shelf life. They tend to go bad after a while. Either they give off an obnoxious odor or their texture changes. And this can result or happen because of 2 reasons. First, you could have what's called hydrolytic rancidity. What happens is water that's present in the food or moisture present in the air can essentially break the ester linkages apart, releasing the fatty acids. To reduce this problem, there's a couple of things we can do. One is to reduce the amount of water that's available by dehydrating our food. Storing it in cool places will reduce the rate of the reaction. And finally, if you sterilize your food, that might remove any microorganisms that are present that might produce lipases, which catalyze this reaction. Second source of rancidity is called oxidative rancidity. This happens because the oxygen molecule can break apart in sunlight and produce oxygen radicals. These oxygen radicals tend to attack double bonds. To solve this problem, if I use light-proof containers that will prevent sunlight from coming in, I can slow down the reaction. I can also put chemical additives in that react with the oxygen free radical to stop the reaction. So that's a brief look at fats, and in particular triglycerides. We'll continue on in our Look at the Biological series by taking a look at carbohydrates in our next program. Thanks for watching, and please don't hesitate to make comments or ask questions.